Thank you so much to Steve McVoy for all he has done for this convention and this community, and for the warm welcome to me as our first presenter. Thank you all very much for coming. I'm excited to be here, as I'm sure you are all as well. And then, without further ado, let us begin discussing my almost 10-year-long, well, more like 5-year-long effort to develop a what amounts to a private cable TV or community access television headend to allow vintage television sets to receive all of the local stations, in my case in Seattle, but could be anywhere, as they would have originally. Before I jump into this, just a quick little bit of fun history on cable TV. As what we know as cable TV, or CATV, was originally community antenna television, because from the very beginning, people would live in valleys, and they didn't want to move to hilltops just to receive television. So a group of residents would get together and each chip in some amount of money to maintain a antenna system, much like this more modern system I have shown here, consisting of an antenna, some amplifiers and sometimes filters, and then a feed to television. So it was only later that the content on cable was different from what you had on the air, and also just pointing out that the idea of not putting rabbit ears or an antenna directly on top of a TV, but rather feeding it from a remote antenna actually dates back really to nearly the beginning of electronic television. So with that, I will get into the motivation for this project. So growing up in Seattle, in a valley by Lake Washington, did not have direct line of sight to any of the television receivers. So from the time I was a little kid, television we had always came from a cable, not from an antenna. We tried, when I was a small child, to set up an antenna on the roof, and it did not go very well. I got a very ghosted picture, which sort of maybe you could make out. So we watched, I think, the 2000 Olympics, if I'm remembering right, on an over-the-air signal, but it never really worked. And then when 2009 came along and the digital transition occurred, naturally there was no more NTSC over-the-air broadcasts, but I had high hopes that the ATSC, or Advanced Television Standards Commission, the current U.S. television standard, ATSC 3 or Next Gen excluded, would allow us to receive television at my home. Similarly, during that time, prior to the transition, immediately after, we received analog cable TV. So we received an actual television signal, NTSC format, over a piece of cable that came into the house. And from the time I was a little kid, I've been interested in analog televisions. And of course, I would plug in the cable and it would mostly work, although not understanding about adjacent channel interference, get a little bit of a herringbone pattern. So the bottom line is that in this modern digital age, antique radios, amazingly, still work as originally intended. They receive the current over-the-air programming, as they always have for over 100 years. This is a 1921 Westinghouse RC, arguably the very first radio sold for consumer use. And they can be tuned using their own tuners to select among present-day radio programs. Antique televisions, on the other hand, or vintage televisions, do not work as intended. You cannot simply place it on a table, put up the antennas, and get a picture. It cannot receive over-the-air programming without an external converter. And the standard digital television converter box that you can get will allow a vintage set to receive over-the-air content, but not really as originally intended. After all, you're just using the tuner of the TV to get one channel, and the converter box itself is doing the tuning for you. So my motivation here with this project, and had been since the digital transition in 2009, was to find a way to build my own converter of some kind. It ended up being essentially a private cable TV head end that would allow me to receive locally in my home all of the local television stations on my vintage sets and enable my vintage TVs to work as originally intended, i.e. to be able to flip through the channels with their own tuners and get a clear picture. So specifically, the goals of the project are and were to allow vintage TVs and even vintage UHF converters, those useless boxes that show up at events like this, to work as intended again. So without, just as if you had a community access antenna and you just wanted to plug that in and receive TV. That was the goal. Be able to create the wow for viewers of my collection by turning on a vintage set and going clunk, clunk, clunk with the original tuner and seeing the local stations come in. For those of you who like to use your sets as a party trick, for people who know just enough, that always gets a, how did you do that moment? I wanted to create a channel plan that mimics what would have historically been in my area. One, well, I don't think we ever quite had channel 1, but 2, every other channel except where there's gaps in the plan. So, 2, 4, there's a gap, 5, 7, 9, 11, 13, because the skirts of the IFs in old TVs are not sharp enough to be able to separate out adjacent channels. That was what cable ready meant. Much later was that they had typically a surface acoustic wave filter that could separate out adjacent NTSC channels. So that was the goal. And as I said earlier, having no adjacent channels was not a feature of most 90s and 2000s analog cable systems. So if you hooked it up to an old TV, you'd always sort of be fussing with the fine-tuning knob to try to get rid of the herringboning pattern. So wanted to fix that. I wanted to include the short-lived channel 1 for my Motorola VT71 and my 621TS, two sets with the channel 1 on it. And I'll talk a little bit about attempting to include the most modern form of television reception, which is streaming, which is, those of you who are watching remotely, is in fact what you're using. So I wanted to see how I could get streaming onto vintage sets. All right. So we're going to work through the rest of this presentation from one end of the system to the other. And the first part of a community access television system is the antenna, because television is a form of radio, receives signals over the air. Not all of this would be applicable to every installation. Obviously, antennas, very specific to where you are, what works best. But given the challenging reception environment that I'm in, I ended up having to have a fairly complicated antenna system in order to get clear reception on all of my local ATSC stations. Specifically, where I'm at, UHF, which is this antenna here, a Channel Master Extreme 1080, which, having tested a very large number of different UHF antennas, I will insist is the best choice that I've found currently available. That's for UHF, which in my locale is actually best received as a bounce off the lake. I was not able to really get line of sight because of foliage and terrain in between. On the other hand, VHF refracts enough around the terrain and isn't attenuated enough by the vegetation that I am able to get line of sight VHF, and that works better than trying to get that as a bounce. So I have a separate VHF antenna, Stellar Labs, also known as MCM Electronics. There's the model number. This is all on YouTube. You can ask me later. But this is a VHF-only antenna, and that's important. I'm trying to avoid multipath here, which I'll talk about in a minute. So VHF only, UHF only. And then I'm combining the two antennas together into one feed using what's known as a diplexer. And what this is two carefully tuned filters, which will allow only VHF signals from the VHF antenna to get into the feed line, and only UHF signals from the UHF antenna. What that avoids is a multipath interference problem, where if you have two antennas receiving the same station from different paths, there's going to be different delays on those two paths, and therefore you'll get multipath interference. I'll talk more about that in a minute. So the schematic so far is we've got VHF coming in this antenna, UHF coming in this antenna. They're coming together at the base of the UHF antenna mast in a diplexer. So the next piece of the system is an antenna preamplifier. Now, there's a lot of confusion among people who are not so experienced with setting up television antennas of the purpose of the preamplifier. To put it very simply, the purpose of the preamplifier is to overcome the loss in the feed line. That's it. It's not going to remove noise that is on top of your signal itself. It's just an amplifier. However, it can add noise. In fact, all amplifiers add noise. The noise figure is a number in decibels which specifies how much noise an amplifier is adding to the existing signal. So the most important parameter in an antenna preamplifier is that noise figure. You want that to be very low. Now, in my particular area, I actually have plenty strong signals. Not way out in the country. It's the multipath interference that gets me. So I was actually slightly less worried about the noise figure here. But I did want that to be minimal. The thing that is important is not to use too much gain, because if you use too much gain, you'll overload the preamplifier and you'll get what's known as intermodulation distortion. And that's where, just like in the mixer of a radio, when you have a non-linear electronic element with two different frequencies entering it, i.e. two different channels, you'll get the sum and difference frequencies out. So you'll have ghost channels appearing where they shouldn't be on your spectrum and interfering with others because of intermodulation distortion. So make sure the gain is sufficiently low, get a low noise figure, and in this particular installation, I added an LTE filter. There are some, with the DTV transition, some of the old television band was reallocated for cell phone use, so blocking that out will help prevent overload of the antenna if there happens to be a cell phone or a cell phone tower nearby. This is the model of amplifier I used. Set some switches inside to set the gain, turn on the FM trap, installed the LTE filter, and that's pretty much it. The one thing I'm going to mention here is I mounted the preamplifier on the UHF antenna mast next to the diplexer. If I was very worried about signal strength and wanted to make sure to overcome the loss in the feed line from the VHF antenna to the diplexer, I could have had a second preamplifier there, but measuring those signal strengths with the spectrum analyzer, I had plenty of signal strength. It was not necessary. Only really the UHF on the bounce was near the limit of signal strength. So I just have one preamp in this system. All right. So from here, we're up on the antenna. We're going to follow the feed line down to the utility room where the start of the head end system, which is the big rack of electronics on the first slide, is set up. The first piece of that head end that the antenna signal encounters is the antenna signal distribution amplifier. The purpose of this amplifier is to overcome the loss in the splitter. We have to take this one antenna signal and split it, in this case, 16 different ways. So recall that 3 dB is half power. So if you had a theoretically ideal splitter, you'd lose 3 dB for going two directions. But in reality, because of impedance matching, it's worse than that. So you actually need quite a bit of gain just to overcome splitting the signal 16 ways. There are many devices that are sold as cable TV distribution amplifiers, which are just amplifiers, power amplifiers, that are wide enough band to cover the whole antenna or cable TV spectrum. They also sell splitters, but devices that combine an amplifier followed by a splitter is somewhat hard to find. Basically, I would have to have had a separate splitter and a separate amplifier, and sort of short of rack space for the cooling needs. So I ended up actually modifying a Drake AC-1686, which is what's known as an active combiner. It's made to do the opposite. It's made to take 16 modulators, and I'll get to what that means in a minute, combine them together into one signal with a power amp to overcome the loss in the combiner, because it turns out that combining and splitting are really the same operation, and they have the same, you get the same loss through the splitter. So it was simple to do this modification. All I had to do was take the cover off of the active combiner. That's this box here. It's opened up. This is the power supply. This is the actual splitter combiner. It's laid out on this circuit board behind the F connector jacks. And then this is the amplifier. So all I did was add these tan cables here to just connect the amplifier to the flip its in and its out, so that it was designed to accept a signal into the amplifier and then split it 16 ways, as opposed to taking 16 signals, put them together, and amplify it. So just a couple of F connectors, super easy. I rebranded the front of this as AS-1686 with a little label maker, just as just for fun, as an active splitter instead of active combiner. The thing to keep in mind here with anytime you're amplifying a power amplifier, or really any amplifier in a system like this, is that it's important to set the gain correctly to avoid overloading the amplifier. So looking at the total power output with a power meter, or adding up the powers of each channel using a spectrum analyzer to make sure that we don't get that intermodulation distortion, which is a real problem. So I ended up using an RF power meter to assure that I got unity gain. In other words, the same amount of power going in, going in comes out each port, and did the math per the data sheet to make sure that that was below the power limit to achieve the intermodulation distortion that I needed. Again, noise figure is less important because it's always the first amplifier in the chain that's most critical for noise figure. We've already amplified this with a preamplifier, so you want a low noise figure, but it's not nearly as important as the preamp. All right. So now we've distributed the signal. So we have antenna, comes down, antenna, preamplifier comes down the feed line, gets distributed 16 ways. Now we have to take that digital signal, and we need to demodulate it. So in this case, demodulate doesn't quite mean just, shift with a heterodyne and filter out the channel you want, because it's digital. So in this case, when I say demodulate, I actually mean, yes, demodulate, bring the single sideband ATSC signal down to baseband, but also decode, digitally decode, to give us back a baseband NTSC signal. Okay, so we're doing the digital to analog conversion step in the demodulator. So your common DTV converter box, which I'm sure all of us are familiar with, would be an example of an ATSC demodulator. So this takes ATSC, gives us NTSC out the other side. I will contest the term that the cable TV equipment suppliers use as referring to a digital to analog converter as a demodulator, but that's the terminology that they use in their data sheet, so I will continue. The DTT 901, by the way, widely available on, no longer made, but widely available on eBay and the like, is just about the best performing ATSC demodulator I have found, having tested just about all of them. So the purpose, again, of the demodulator is to tune in to a single ATSC channel, demodulate to digital baseband, decode that digital baseband to video, and then modulate, well, not really modulate, but decode that digital video and encode it with a digital to analog converter as NTSC. You'll also see ATSC demodulators, which put out digital formats such as ASI, asynchronous serial interface, which is a way of sending digital signals around inside a cable TV system, or some other digital format. But in this case, we're referring to ones that give us baseband NTSC. In this whole system, the ATSC demodulators are the most critical part. As I said, where I'm at, I have a really hard time receiving ATSC. There's supposed to be improvements with ATSC 3 that reduce the effects of multipath interference, but as it stands now, it's quite a problem. So the basic idea of multipath is if we have one transmitting antenna and one receiving antenna with a hill or something nearby, we can have one direct path from the transmit antenna to the RX antenna, and then one or more, sometimes many, indirect paths where it comes off the transmitting antenna, bounces off the hill or a building or a lake, whatever there is that would be in between the two antennas, and then be received as the RX antenna. And you can see the path lengths are different. The indirect path is longer, which means there's a phase shift in the received signal. You get two copies of the same signal, time shifted, but on top of each other. And that makes it very difficult for the ATSC demodulators to demodulate, to decode the digital signal. The way this is corrected is with a filter that's called an adaptive equalization filter. And the way this works, it's a digital filter, and you can imagine conceptually having a delay line and tapping that delay line to pick a specific delay, and then having many such delay lines and adding up the sums, each with an appropriate weight. And if you do that, that's exactly the opposite of what happens here, where we have different weights of different delays, and so you can cancel out the effect of the multipath and give you a clean signal that can be easily demodulated. But the algorithms to figure out where those taps should be and what the gain of each of those taps should be is not trivial. And so there's been a lot of improvement, a lot of variation between vendors of those demodulators. So, as I said in my testing, the good old-fashioned Zenith DTT 901 performed just about the best, but it's not a rack mount unit. It's difficult. Whenever you try to do 16 of something, it gets pretty difficult to program everything correctly if it's not made to be used in a rack mount system to cool everything correctly. So I wanted to use professional cable TV, CATV equipment for this. So I ended up trying several different brands of rack mount ATSC demodulators. So this is the first one I used. This is the Blonder Tongue AQD system. It was introduced in about 2006, right when ATSC was starting to come on the air, at least in an experimental sense. I don't know that date exactly, but it's somewhere in that ballpark based on the date codes on parts and on boards. It's very early, runs very hot because of the limited, lower tech electronics available at the time. And I had very poor reliability with these. I actually had 3 or 4 of them fail in my system or were failed when I bought these used. I'm not buying it new, it's horribly expensive. I'm an electronics engineer. I work on circuit board design for a living, so of course I get curious what the actual failure mode is. Turns out that it's this chip here, which is an ASIC, or application-specific integrated circuit, which is used by the demodulator to do the actual digital decoding. What happens with these is that the plastic part of the chip that you see gets hot, and the board underneath it less so. And there's a whole array, tiny little array of balls or blobs of solder, called solder balls technically, underneath this chip, which make all the connections. So if you have a different thermal expansion coefficient of the plastic part and the board part, the two of them will strain against each other every time it heats and cools, and that will eventually crack the solder balls. So I was actually able to fix a few of these AQD boards by removing those chips. I found some replacements in China and soldered them on, but it was not very reliable. They run hot. They did not receive very well in my area at all. It was a real struggle just to get all the local channels to come in at all. And it's pretty hard to configure. It uses this little control box with little arrow buttons, and it's pretty primitive. I also tested the newer, so the AQD system's been discontinued. Blonder Tongue still sells a version of their MDDA system, which allows you to fit more of these modules in the rack. It's only a 2U instead of a 3U tall rack. Widely improved, but unfortunately still uses this same or very similar ASIC, so I did not see any improvement in the adaptive equalizer, so I was still having a very hard time receiving all the local stations. So that was my first attempt. I got that done in late 2017, right after coming home from living out in Boston. Ran it for a bunch of years, and then in 2020 decided that I really wanted to upgrade. I had had enough of these blonder tongue AQD modules fail. I wanted something better. So after doing a lot of research, I ended up settling on the Drake DAD 860s. The adaptive filters are not quite as good as the Zenith, but they perform much, much better than the blonder tongue AQD. Get a stable picture pretty much all the time from turn on. It does not use failure-prone capacitors. There are electrolytic capacitors here, but they're all good quality and they're all through-hole, not those horrible little surface mount ones that always seem to leak their guts out. I found them to be robust and reliable. They do still have a large ball grid array ASIC in them, but it doesn't run as hot. And I think they've gotten the solder tech improved a bit. These are from more like 2010. And best of all, it has a serial port on the front of each unit. You can see them here. That's the little silver connector. And those plug into any Windows computer. So you can program the channels manually from this very nice little Windows GUI. You can set the frequencies. You can manually add a channel. You can set up a configuration file for, your local area and copy it to all of these. So way, way easier to deal with than the blonder tongue ones, and even easier still than the home, boxes. So really a very nice system. The other nice thing about this is, I don't know if you can see, but these same racks, on the left here, there's a controller module, which is two of these little, mini units wide. And then there's a power supply on the right, and the power supply will drive both these DAD 860 demodulators as well as the VMM 860AS modulator. So I could go demod, mod, demod, mod, demod, mod, which avoids a lot of long cables running from one big rack mount unit to the next. So a nicer system all around. I'll also point out that there is a Pico Macom MPD, which is also a rack mount system, uses the same form factor, different control box, that's proprietary. I don't own one. I'd like to, but I couldn't find any inexpensively on the used market when I was setting this up. The challenge, I have not been a huge fan of Pico Macom CATV equipment. I prefer Blonder Tongue and Drake, but both U.S. companies, Pico Macom's Taiwanese. But the Pico Macom units are newer. They might have a better adaptive filter. So that's just a heads up if you're building something similar. You should probably compare those to the others in your area. All right, so having settled on a demodulator, the Drakes, the next thing was to figure out how to do the aspect ratio. So one of the most frustrating things about trying to use vintage sets with modern content is that modern content's designed for a different aspect ratio, a 16:9 aspect ratio as opposed to a 4:3 aspect ratio. Also, modern TVs do not trim the edges of the picture as vintage sets do. So between both of those, you got to do some sort of scaling to get this to work. And there's no perfect option here. Fundamentally, you can't simultaneously see all of the picture and not have some distortion or black bars. So the choices are, we can stretch the picture, which distorts a 16:9 picture to fit in a 4:3 screen. This is just plain a bad idea. Don't do it. Also, we'll comment that if you have 4:3 content, which was broadcast with black bars, and you squish it, now you have squashed 4:3 content, which still has black bars. So, no. The next choice is letterbox. This is what most demodulators default to. That's where you put black bars on the top and the bottom so that you see most of the 16:9 picture. Notice the mask on your vintage set is still going to cut off the edges, and therefore you're still going to lose something on the sides, even with the letterbox option. A few things that are troublesome with this, with vintage sets. Vintage TVs were not really set up to have very large contrast gradients horizontally across the picture. Some of the more primitive sync circuits can get a little bit confused on those black bars. I see some of the audience members nodding, you know what I'm talking about. So that can be an issue. It also makes 4x3 content, which was broadcast with black bars on the sides, now be a small picture with a black frame around it, which just looks really dumb. Sorry, too. But it really does not look like a good look for the vintage set. So honestly, as much as I sort of hate to cut off part of the picture, the best option is to crop it. Just to crop everything. Because for the most part, if you're going to lose being able to read some of the text on the edges of the screen, you're probably going to lose that anyway, even if you do your black bars because of the masking on some of your sets. And for demoing the TVs, it just looks a lot better to have a full screen picture. And for most content, you have a politician talking, you have the, you have your TV show. The center of the screen is where the action's at anyway. So just cropping the edges off works the best in my experience. The last option is a feature called AFD, Automatic Format Detection, which uses codes that are broadcast with some programs to automatically decide between letterbox and crop. In principle, this is a great idea and sort of solves the format problem. The reality is that in this day and age, the TV stations are so disinterested in 4x3 users that the AFD codes are usually meaningless.
Common issue I've seen is that they're broadcasting a vintage show that was originally 4x3. They'll stick text or graphics on where the black bars would be and transmit it as 16:9. So
yeah.
You have to crop it to make it look right.
Exactly. So I tried AFD. I was really hopeful. I found it a waste of time. So go with crop. My recommendation. All right, so we've got our antennas, our preamplifiers, our distribution amplifiers, our demodulators. Now we need to modulate because the whole goal is to get this on vintage sets. So this is the fun part. There are many models of NTSC modulators available. Unlike the demodulators, it's a pretty standard thing. Every cable TV system had them. I'm not going to be able to go through all the options here, but I'll go through some of the main differences between models. The first point to realize here is fixed channel versus frequency agile. So fixed channel modulators would be what would have commonly been used in older cable TV head-end systems. Each one has a SAR filter in it that's tuned for exactly one channel. And a crystal, you get what you get. They're less expensive, they take less power. Because of the custom-tuned SAR filters, they typically, I think always, but not totally sure, I haven't looked at all the models, produce true vestigial sideband NTSC. I'm not going to go into the technical details of what that means, but it's a true, perfect broadcast quality NTSC signal. They're hard to find in the desirable VHF channels because most cable TV systems, most of the channels were higher than that, and the VHF ones are in demand. And it's inconvenient not to be able to retune your system. It's really sort of a pain. So I recommend using agile modulators, which are more expensive, depending on the model, may or may not produce true vestigial sideband NTSC, not that I think we really care for the most part with vintage sets, but they're much more versatile and convenient. Next thing to keep in mind is the physical size. The older models were typically 1U per channel, which if you're trying to put this in a compact space, gets very large very fast. The newer units, like the demodulators we were looking at earlier, allow 12 modulators per 2U. So I prefer that newer form factor. Stereo or mono sound. As far as I know, there's not really many problems with using stereo sound with that sub-carry-on vintage sets, so I opted for it just so my 90s sets would get true stereo, which is kind of fun. So specifically, I've used both Blonder Tongue ACM 806. The 806 is the highest frequency that it will transmit, way high in the UHF, where again, we're not that interested in typically as vintage enthusiasts. And the Drake VMM 860. Both work fine. I found that the Blonder Tongue units did not require recapping of all the SMD capacitors, while the Drake units did. However, once recapped, the Drake units were actually more reliable, quite a bit more reliable than the Blonder Tongues. I had several failures in the Blonder Tongue units. May have been due to inadequate cooling on my part, plus the units were used when I got them, so take that with a grain of salt, but both are good quality. I'll just point out that there are 5 surface mount capacitors that need to be replaced for long-term reliable operation in the Drakes. Before you do that, the video or audio was weak on some of them. Others, the digital display wasn't quite right. But you just replace those capacitors. I mean, if you're good at capacitor replacement, it's not that hard. And these will come right back to life. All right, so after the modulators, we have the amplified or active in the CATV speak, combiner. And again, this is so that you can overcome the loss due to the splitter combiner, which inherently has loss, in order to maintain impedance matching, so-called magic T. So the purpose of this is to overcome that loss in the signal combiner so that you get the correct amplitude, sufficient amplitude of each of your channels out on your final cable TV system. Again, there are many, many models available. I was trying to build this system up as pretty much a fully Drake system. So I used a Drake AC 1686, same model I modified to make the active splitter. Again, the big issue here is intermodulation distortion, just like on the antenna side. But here, because it's an analog signal, it's not masked at all. So you'll see it on the TV sets. So basically, if you have excessive intermodulation distortion, you'll see a weaker version of some channels will appear mixed up and offset in between other channels. Ghosting, herringboning, that type of thing will start to show up. Not good. The important spec to look for in the data sheet is IP3, the third order intercept point. Again, I'm not going to go into the technical detail of what that means. It basically, lower numbers better. I'd say a good power amp should be negative 60 dB or so on this IP3 point. And again, really critical that that gain be adjusted correctly to assure that the amplifier is not overloaded per the maximum output spec. Basically, if you can get 1-to-1, so the same amount of power coming out of your modulator that's coming out after the active combiner, you should be set correctly. You can see that with a spectrum analyzer. The thing to note here is the specification, the data sheets for the maximum output can be rather confusing, as it's usually given as a signal level in dB microvolts or dB millivolts for a channel, for any given channel. But in reality, what matters is the total power, which would be the sum of the powers in the individual channels. Because of the dB units, you have to be a little careful with that. So just recall that if you double the power, that doesn't mean you add the dBs. That means for every doubling, you get 3 dB. That's how logarithms work. So just you have to pay a little bit of attention to make sure that you're not exceeding that maximum power output. Very, very important. All right. Recall one of my goals was to recreate the famous Channel 1. It turns out that there is one specific model of blonder tongue agile modulator, which is sophisticated enough, or maybe not sophisticated enough, that it allows you to tune the various stages of the modulator, tune the frequency of the various stages of the modulator manually with a set of dip switches. And because of this, some smart people who were not me figured out how to adjust those dip switches to program it to be exactly the right frequency for the historic Channel 1. So the key thing here is that you want a blonder tongue AM series modulator, but it has to not have an LED display. If it has an LED display, it won't have the dip switches and it won't work for this. There were multiple different models of the so-called AM series made. The first number is a power output spec, so the 40 puts out less power than the 60. Don't really care, frankly. And the second number is the maximum output frequency, so basically the highest channel, so 450 megahertz or 550 megahertz. Any of those will work fine for this application, but again, can't have an LED display and it has to be a blonder tongue AM. There are other modulators out there with dip switches, but most of them that I've seen, and if someone knows of another one this will work with, I'll be all ears, but most of them, the dip switches just sort of set a channel number. They don't actually let you tune the frequency of each stage of the modulator separately, so you can't hack them in this way. The next thing to keep in mind is that if you're going to put Channel 1 on a cable, private cable system like this, it needs to be on its own switch. And that's because a lot of modern 1970s and newer solid-state TVs with UHF use a frequency for the UHF intermediate frequency, which is very similar, to the old channel 1 frequency. So what you'll get is a whole bunch of nasty herringboning all over your picture on some unrelated channel when you have your channel 1 modulator on. So you just need to make sure that when you're demoing a newer TV, you turn off your channel 1 modulator and only turn it on when you actually are demoing a channel 1 set. So a little annoying. I was sort of hoping I could leave it on all the time and just have it be there, but not technically part of the channel plan. And then the next comment I'm going to make here just real quick. I didn't want to dedicate an entire local channel just to channel 1 because 90% of my sets couldn't even receive that. So I just wanted to split one of the local channels. Historically, channel 1 was typically used for like educational or local programming. So I picked the local lower power, my area, channel 19, UHF station to use for this. And I wanted to send that one station out, both a UHF modulator, a standard little rack mount NTSC modulator, as well as channel 1. But to do that, I had to do a couple of things. First off, I had to have a splitter for the video signal. Remember, video signal is 6 megahertz wide. It's it's RF in its own right. And I wanted the same video level going into both modulators so that channel wouldn't have a weaker video signal. I tried turning up the gain to compensate and ended up deciding it made more sense to use an active video amplifier splitter. So I actually designed this little board here on the right, the one on the left. You can sort of see, looks like that. That just takes one demodulator video output on an F connector and amplifies it and splits it in an impedance matched manner, so you get the correct 75 ohm output impedance on two paths. So one again goes to the modulator for the UHF channel and one for the channel 1 modulator. Similarly, for the audio, the channel 1 modulator, these Blonder Tongue AM series typically are not found with the stereo option, and frankly stereo sound on channel 1 makes no sense. So I wanted a mixer that would mix down the stereo audio to mono without do that in a technically correct way so that you wouldn't overload the amplifier drivers on the driving circuit. So you could just use a resistor divider. I ended up using a little op-amp circuit. That's what this one on the right is here, and you can see that hooked up right here. So I just used RCA splitters to split the audio, and then this is a high impedance input here and then a down mixer. So it mixes the stereo down to mono. Very nice little board. And these can be powered, you can see here, off of the same power 12 volt and 5 volt power cables that are powering everything else in the system. So I just made a little splitter cable there to do that. All right, so that was channel 1. A lot of fun, kind of a gimmick, but kind of fun to see channel 1 work. The next thing was channel streaming. I'm going to keep this real brief. I was not able to make this work very well. I set up a sync detect video switch to switch over my channel 3 between channel 3 over the air, that demodulator, and a Roku streaming box when I remotely turned on the Roku box, because you can do over Wi-Fi these days. That part worked. It was really cool because I could take my phone and I could open up the Roku app, and even though my cable TV system's down in the basement and the collection's upstairs, I could do the Roku from my phone, and so it would show up on the vintage sets. The problem is that the Roku really has very, very poor support for 4:3. It likes to make a distorted, squashed picture for many video sources. The menu is not designed for a 4:3 screen and can be very hard to navigate. And yes, I'm setting the menu setting inside the Roku to 4:3. Also, just the quality of the NTSC video that it produces isn't great. Unlike some older devices that I have had in the past that used to work with streaming services like a Nintendo Wii or the old versions of the Roku that no longer will connect because they've been obsoleted, the video output was just not great. Also, the Roku Express Plus has been discontinued, and neither Roku nor anyone else actually makes a streaming box that will put out composite NTSC video. The right solution here eventually will be to build a better HDMI to composite adapter that will downscale 1080p to 4:3, do the cropping, all of that, but I also have a full-time job and a girlfriend, so I have not designed that yet. When I do, that will be a presentation here, I promise. But for now, streaming works, but sort of so-so. Some other important considerations here that I didn't touch on in detail. Cooling is critical. My first rack built out of blonder tongue parts, I did not have enough fans in there, and it really ran hot up near the limit, the temperature operating limit that the data sheet specified, or above it. That probably contributed to the premature failure on some of my units. As I said, I've seen some fail even, used in commercial environments, so not the whole story, but definitely part of it. You can see here in my current system with the Drakes, I'm using these little 1U fan boxes that blow air in between each section of the rack. That helps a lot. I also put a cooling fan in the room, exhaust fan that circulates air to make sure that the utility closet that this is set up in doesn't get too hot, and that fan kicks on when I turn on this system. I set up remote control switches, which allows the system to be shut off remotely when not in use to just save on electricity and runtime on the equipment. Power conditioning is important. You got a lot of expensive electronics in a rack. Surge protector, good idea. All the signal distribution and all the wiring, plumbing, as I joked, with these little F connectors and these stiff cables, really important to get clean signals on your NTSC channels without the TV accidentally picking up ATSC that's broadcast on the same frequencies. Copper braid cable's the best, but really expensive per foot. I found that the quad shield is almost as good and reasonably inexpensive, but don't use cheap cable. Buy from Belden specific CATV quad shield cable, and always use compression connectors. That's the kind where you stick the pin in there, and you have a special tool that squashes the two ends together, makes a watertight seal. Very, very important. Then another little demo. They make Leviton actually makes these nice little outlets, which have cable TV outlets that have 2 jacks on them. So I have one that's labeled antenna, is coming out of my private system. And that's for the NTSC output, and then the cable is just our Comcast cable. So we can have both for the new TV. Finally, a cable TV spectrum analyzer, defined by having a 75 ohm input instead of a laboratory spectrum analyzer that would have a 50 ohm input, is very useful for tracking things down. So good thing to invest in if you're doing something similar. This is mostly for those of you who are going to want to get the slides afterwards. You can study this, but this is a block diagram of my system. We have the VHF and the UHF antenna connect to the diplexer. There's the LTE filter, notches out the LTE. There's the antenna preamp. This is the amplified splitter for the antenna system. The 16 demodulators, the 16 modulators, the audio mixer, and the video amp and splitter split off the video and audio from one of those ATSC demodulators to go to the channel 1 modulator, and then the 17 signals go into an amplified combiner down here, which gives out NTSC. So that's the diagram. Again, some things are not shown, but for the sake of one slide. Finally, here is a photo of the converter system as set up. This is our utility room where we have our hot water and heat equipment as well. You can see at the very bottom of the screen here, this is my spectrum analyzer for testing. It's currently hooked up to the test point on the antenna distribution amp. I have 3 Wi-Fi switches here that allow me to turn off the whole system power, the Roku, and the channel 1 so that I can remotely control this. We have the 16-channel combiner and amplifier. This is the so-called active combiner. We have the modulator for channel 1 right here. Then we've got the 16 ATSC demodulators and NTSC modulators along with their power supplies and controllers. So that's the main bulk of the rack. And you saw close-ups of those earlier. Those are the Drakes. We have the antenna signal power amplifier and splitter. This is the so-called active splitter. Up here, a surge protector and power strip. This is the Roku and video switch box, and I am using this is the very first TV I ever personally owned. It was my TV. It's a 1980s Freedom brand made in Korea, black and white TV. Very convenient to have on the system for testing as you're tuning everything up. All right, so without further ado, here we have examples of live shots off of various vintage sets on this on my system. Here is my 1949 Admiral. You can see this is a news broadcast. You lose a little bit of the text because of the cropping, but the picture is otherwise nicely framed and very clear. Here's a news broadcast on a 57 GE. That's the famous 9T001, the one with the CRTs that always go soft, so it's a little soft picture, and a 56 Emerson. The picture's not really distorted. The camera was a little bit off angle. This is my 47 Motorola VT71. Here's a 85 Casio LCD. To get this shot, I actually just touched the antenna to one of the to a live cable because it doesn't have a remote antenna input. And just to give you an idea here of the what this set's able to do, this is a modern 1999 Toshiba, all recapped, and you can see it's a very bright, clear color picture. So very little interference, looks digital. A lot of fun, really enjoy this. I think it adds tremendously to my vintage TV collection, and I would encourage those of you who are like-minded to please reach out to me for help in building something similar. I can provide additional details, schematics for the boards I built, model numbers, etc. Please contact me through my website at desarodesigns.com. That's my consulting business logo. And last but not least, here is a link to a very long album of photos. I'd like to thank my dear mother very much for helping me with the photo archiving and photography through all of this. This is to you, Dana, and thank you to Kayla, my girlfriend, very much for helping me out with this presentation and tolerating my TV collection. So same goes to Mom and Dad. A lot of it's just at their house as well. So without further ado, are there any questions?
How far are you from the TV transmitters, point to point from the transmission?
Good question. We're only about 10 miles, I think roughly, from my house to the Capitol Hill, where the transmitters are. Might be a little more than that. I'd have to look on a map to give you an exact number, but it's not that far. The big issue is Seattle's very hilly, and there's multiple layers of terrain between them and us. Question in the back.
Yeah, the cropping takes
Yes.
place in the demodulator ASIC, that's setting over there?
Yes. So the demodulator handles the cropping internally. There's a setting you can use through the little menu on the control box or through the Windows application. And it will handle that in its ASIC. Questions?
On the modulators.
Yes.
Are you finding any HRC type stills out there? By HRC, I'm referring to harmonically related carriers.
They certainly exist out there. That's a good point. I've tended to avoid them and go for ones that can be programmed for broadcast. For the most part, the agile ones can be programmed for the various cable TV frequency plans as well as the broadcast plan. So that can work. I know there were some that were only the HRC.
That was the first cable system I worked for. We built it at HRC to prevent composite triple beat.
Yep.
Also, if you're looking for a inexpensive demodulator to go from HDMI to composite video and audio, there's one at, believe it or not, Walmart online.
Yes,
And
I'm aware.
the only thing it requires is an external 5-volt power supply.
Yeah, I'm aware that I have that unit along with several others. At least in this, it's changed in the last few years. It does not handle the aspect ratios terribly well. Question in the back.
Do they have a mandate yet for when 3.0 has to be?
No, I've been following that very closely. and someone here may know more, but I'm aware that the ATSC-1 is still the FCC mandated standard, and I don't know of a hard date. Again, you may have a better answer.
Well, that's a good question. So I think broadcasters would very much like to shut off 1.0 at some point. The FCC about 2 weeks ago at NAB announced they're going to start studying that question. So it's probably 5 to 10 years away when 1.0 goes away.
Thank you. Question?
You have 16 ATSC demodulators.
Yes.
Do you have 16 basic channels with all their sub-channels, or do you have like 3 or 4 stations and you're encoding all the sub-channels?
Very good question. In the interest of time, I'm going to avoid going through the whole plan, but the short answer is I have all but 2 of those are actual local base stations transmitting their base content. The last couple are sub-channels that are particularly desirable.
Okay.
Any other questions? All right. I'd like to thank all of you again for being a wonderful audience, and welcome Mike up for his presentation.